Alright, so we're going to look at section 11-3 on contingency tables in this video here. So key concepts in this one is that we consider contingency tables, or two-way frequency tables is another name for them, which include frequency counts for categorical data arranged in a table with at least two rows and at least two columns. Now, in part one, which is really just the part we're going to look at, we present a method for testing the claim that the row and column variables are independent of each other. So there's some kind of association. And since we're working with categorical variables, just want to make a little note here. In a way, this checks to see if there is an association of some sort. So just to recap, Chapter 10 looked at associations of quantitative variables with all the correlation and regression. And so now in this section 11-3, we're looking at associations of categorical variables. Okay, so on to this part one. All right, so for a definition, a contingency table or two-way frequency table is a table in which frequencies correspond to two variables. And one variable is used to categorize rows, and a second variable is used to categorize columns. And then contingency tables have at least two rows and at least two columns. They can have more of each. So below here is an example, and so it's a contingency table summarizing the results of foot procedures as a success or failure based on different treatments. So your two variables can be like the different types of treatments for one variable, and then the success is something kind of like the other variable. So there's four types of treatments here, and then success, you can just describe it as it for sure was a success or it was a failure. And then notice there are frequencies in each of the cells here for depending on if it was, say, after surgery it was a success, or after surgery 12 were a failure, and so on. And so what we're going to use in this section is called a test of independence. So test of independence tests the null hypothesis that in a contingency table, the row and column variables are independent. So, and we see if the, in this case, the treatment and the success are independent of each other or not. And just for the notation, capital O still represents our observed frequencies each time in the contingency tables. Capital E will still represent expected frequencies. And then now we start using a lowercase r to represent the number of rows in the contingency table, and lowercase c to represent the number of columns in the contingency table. Now, some requirements for these contingency tables are similar to the previous section. The sample data needs to be randomly selected, and the sample data should be represented as frequency counts in the two-way table. Then for every cell in the contingency table, the expected frequency must be at least 5. And again, there's no requirement that the observed frequencies must be at least 5. They can be less than 5, even 0. Just the expected frequencies for each spot needs to be at least 5. And the way the hypotheses and test statistics will work out for these types of tests is the null hypothesis. It's always going to be the same. The row and column variables are independent, and the alternative hypothesis being that the row and column variables are dependent. And to find the test statistic, it's the same way as we did it for the previous section, where to get that, we take all the observed values and subtract the expected values, get those differences, square them, divide those differences by the expected value, and then add all of those up for all the observed and expected values. Then we'd get our chi-square test statistic. Now what's different this time is to get our expected values, we do a row total times the column total for whichever spot we're in, then divide it by the grand total, which I'll show kind of what that looks like in a little bit here. And we can still use p-values and critical values to make our conclusions. So p-values, we want to be using technology to find those. And I recommend on StatsMedic, there's an applet called chi-square independence that will be good. You can also use Google Sheets to find the p-values, which again, I'm going to make a separate video on how to find those. And for the critical values, you can use that chi-square table, which is table A-4. And this time, instead of using n-1 or k-1, use r-1 times c-1 for the degrees of freedom. So take the number of rows, subtract 1, take the number of columns, subtract 1, then multiply those two numbers together. That's your degrees of freedom. And similar to the last section, these tests of independence are always right-tailed. Now, as for expected frequencies, so referring back to slide 6, which is a slide with the table there, then let's get back there. All right, so the observed frequency is 54 successive surgeries, and this just goes through a little bit on how we get the expected frequencies. So again, you take the first row total, which was 66, then multiply it by the first column total, which is 182, divided by the grand total of 253, and that's how we would get 47.478 for the expected value. And it's totally fine if we have decimals for the expected frequencies. And just to reiterate here, so I can look at the total of the column, total of the rows, and to get the expected value that would go, expected frequency that would go in this cell, I do that 66 times 182, since that's where those meet, divided by the grand total of 253. And that's how I got all these numbers here for the expected frequencies, in which I use Google Sheets to find all these. And again, I'll show how to do that in a separate video. But essentially, say I want to find the expected frequency for surgery and failure also, I would just do 66 times 71, divide that by 253, and so on for all of these. So like for example, expected frequency here for success and non-weight bearing cast for 6 weeks, just do 182 times 73, all divided by 253. And I should end up with all those expected frequencies. Alright, now continue with this example. Does it appear that the choice of treatment affects the success of the treatment for the foot procedures? We're going to use a 0.05 significance level to test the claim that success is independent of treatment group. So success being independent, or just knowing that the two variables are independent. So this little requirement check, based on the study, we'll treat the subjects as being randomly selected, and the results are expressed as frequency counts, so we're good there. And the expected frequencies are all over 5. So all these are over 5. So we're all good there. Then, all right, so we start with, again, knowing that the null hypothesis is always that the variables are independent, and the alternative hypothesis being that they're dependent. So now we use that significance level, still 0.05. And we would go through that process to find our test statistic of just taking all the observed values, subtract the expected frequencies, square that, divide it by the expected frequency, then add all those up for each pair of observed and expected frequencies, and we would end up with 58.393 for the chi-square test statistic. And we can use technology to find the p-value is going to be very small for this one, so less than 0.0001. And so since that p-value would be so small, again, just like any other hypothesis test, we would reject the null hypothesis. So we're rejecting the idea that they are independent. And now, so that's using p-value method, and we could also use a critical value method. So again, to use the critical value method, you do the number of rows minus 1, so 4 minus 1, times the number of columns minus 1, so 2 minus 1. So we'd have just 3 times 1 to get that degrees of freedom of 3. And I know that significance level is 0.05. So when I look on the chi-square table, then I look in that column, degrees of freedom 3, so 7.815. So I can make sure that it's going to be my critical value. And since our test statistic is 58.393, that's another way you can confirm that. And since it is much bigger than our critical value, in what are always right-tailed tests, we reject the null hypothesis as well. All right, I'm going to show a StatsMinute applet that you can use to find that p-value and test statistic. Just all get the same conclusions. So again, it's under YouTube and other tools, and again, you can find the chi-square table here if you need it there. I'm just going to open up the StatsMinute applets. And so the applet you want to use for these types of problems are under traditional inference, and you want to use this one, chi-square independence. And for this, you can add rows and columns for whatever you need, depending on how the data is set up. So to save some time, I typed it in already over here with the added rows, and then all that information typed in from that problem. So all I would have to do is just do begin analysis. Gives me some bar graphs, which I don't really need those. All I need is down here at the bottom under perform inference. And so notice it's just doing a chi-square test for independence. I just click perform inference. It gives me that same test statistic of 58.393. And it's telling me that p-value is less than 0.001, so it's very small. And I could use that to know that it'd still be less than 0.05 for that p-value. So just knowing again that I'm rejecting the null hypothesis. And something that's nice with this applet is actually it gives you the expected counts here as well. Those ways you can use that stat-semantic applet for test for independence. All right, and just to interpret all that conclusion a little bit, it appears that success is dependent on treatment, since we rejected the null hypothesis of independence. And this is just a little extension here of that particular context. So although this test does not tell us which treatment is best, we can see that the success rates of 81.8%, 44.6%, and so on suggest that the best treatment is to use a non-weight bearing cast for 6 weeks. And that's just because from that table of values, you got the biggest percentage in this row. That's all that is. It's just kind of a extension of the context there. And then just finish off, there's just a little visual, just kind of emphasizing some of the same ideas from before. So basically, if your observed frequencies and expected frequencies are close, then that's meaning you're probably going to end up with a large p-value, and so you'd fail to reject independence. Then if the observed and expected frequencies are far apart, you're probably going to be ending up with a small p-value, and you're going to be rejecting the idea of independence. So still similar ideas to the previous section.